be a little, I would say, uh, a little bit of tool based, and then I would also give some, what do you say, like example of how I use network traffic analysis for some research that we did. So usually it's good idea. So in when we talk about network traffic analysis, what we are really saying is that we want to observe the data that is going on the on the communication links, and then try to use it for certain kinds of applications, right? So for instance, one possible application is to monitor if all the devices in the internet, I mean, all the devices in your network are up and running, right? So for that, you need some sort of a network level traffic analysis, or you want to look at if you want to know if somebody is trying to send you a malicious or a malware, or somebody is trying to scan your machine for open ports and things like that. So this is a broad area of a work which basically I would say there are two applications of network traffic analysis. One is management of networks. The other is about managing the security, right? So you're trying to find out any security issues. So the outline of my talk will be like this. I'm going to talk about what are the types of packets you can capture, give a brief about layers and the fields that you're interested in. Then I'll give a brief idea about what kind of packet analysis you might be doing. Then I will talk about flow analysis and attacks. I'll be actually talking throughout this session. I'll be talking about the attacks. Okay. So by the way, I won't be able to access the chat window. So if you have any question, it's better that you actually ask me. Okay. All right. So okay. So generally, when we capture frame, when we try to capture network traffic, what we are actually trying to capture is the link layer frames. Okay. So as I'm assuming most of you are familiar with these with the different layers we have in the network, right? So we're talking about those kind of things. So let me give a brief about how this is actually done. So basically, we do network traffic analysis to manage networks, and also we basically how do we capture the data is that we actually use a packet capture tool that sniffs on a given network interface. So we have to assume here that the packet capture tool that is trying to sniff on the network interface, it is running on the same computer as the data is going and coming in, right? Or it has access. So the tool has to run on the same device to capture the data, right? So you can do remote captures also from a remote switch or a remote device, but that requires the switch to actually provide you that kind of capability. Okay. And if you want to try network capturing on your own device, then typically you will have to be a super user.
Hello.
Yes.
Hello.
Yeah. Hello. Hello. Was there a question?
No, sir, you can proceed. I think there was somebody who was interrupting.
Yeah, that just scared me. Okay. So basically, if you are trying to capture, then you must have some kind of a root privilege, or you have to be the admin of this machine. This is because the network interface card happens to be a privileged resource, right? So it is generally not accessible to users as such. So you have to make a system call, and yeah, the operating system will have to give you access to that particular device. Okay. So this is the reason. This is so when you try to download any of these tools, then you will actually see that they will actually get installed with those kind of privileges, and they will warn you that they will be getting installed with the admin privileges. Okay. So there are some popular tools out there. Wireshark. If you have done network capture anytime, this will be fairly straightforward for you. So there is Wireshark, which is the user interface GUI based Windows based tool. Then there is a command line. There are actually two popular command line versions. Wireshark, T-Shark is actually a version of Wireshark, which is command line based. And TCP dump is actually one of the most popular open source tools out there that actually gives you a lot of capability. And this is actually what I'm going to say used to show you how data is captured. You can actually write your own network capture tool with the help of the libpcap libraries or the pcap libraries or packet capture libraries, right? So these libraries actually let you write all the API. They provide all the API calls that are like to make these packet captures.
Base Brew, please mute yourself, please.
Thank you. If you want to process data, you can use Python has like PyShark, and it has a lot of like dpacket, dpkt libraries, which actually, you know, if you give it a packet capture file, it will process the individual packets from the packet capture file. So so these scripts and all that are, you know, very you know, easily available, and you can download it and all that. But the key part in network traffic analysis is not whether you can capture the data or not. It is how you analyze the data, right? That's why it's called traffic analysis. And generally, it's a complex, error-prone process, because if the analyst doesn't know what he's trying to look for, he is not going to get anywhere. Okay, he won't know what to solve. Okay. Second thing is these days, what makes things very difficult is that most of the traffic is encrypted. So that means if traffic is encrypted, you cannot actually detect if some website is sending you any malicious packets or something like that, right? So there are some issues with packet analysis. So here's a brief about the application layers that you know, generally we are interested in, and some protocols at these application layers. So so we have I mean the network layer. So this is a TCP/IP stack. I'm not going to consider the OSI 7-layer stack because what is out there is just the TCP/IP. And TCP/IP stack has 5 layers. Of course, I showed only 4 layers here. The 5th layer is the physical layer, where we talk about all these, you know, all wireless, wired, and all the different communication medium. In the application layer, we have different kinds of interesting protocols like HTTP, HTTPS, DNS, SNMP. These are all interesting protocols in terms of traffic analysis. Okay. DNS, for instance, analyzing DNS or analyzing, you know, PT, this BGP. These are the kind of things that people are usually interested in. And a transport layer, you have different kinds of protocols. TCP and SCTP are stream protocols. That means they are connection oriented and treat the data as a stream of bytes. So that means they are reliable and they don't lose data. UDP is actually a datagram oriented protocol, or it's like a connectionless protocol, and it doesn't have any reliability or any other mechanisms to make it robust. But if you look at modern browsers, they actually use UDP very heavily. So that's but they build on top of UDP. So they use reliability on top of UDP. But these are interesting protocols at this layer. At network layer, we're interested in IPv4, IPv6, ICMP, and IPsec. At link layer, we are interested in these kind of fronts. In fact, the last layer is where you actually end up capturing the network packets, because as the data comes from the application layer, usually the user actually, you know, wants to send a message. He will invoke one of these protocols, right? So that means it will come down from the application layer, trickle down to transport, trickle down to network, trickle down to link layer. So every layer will add its own envelope or a header on top of the message passed down from the upper layer. So transport layer will add something to the application layer, and network layer will add something to the transport layer, whatever message is coming. So, and the link layer is the final envelope that adds on top of the network layer datagram. So this is what actually gets captured. So generally, when you are trying to capture data, you are actually trying to look at the link layer frames. Okay. So here's a good example of where network traffic analysis can be useful, right? Let us say, how many of you heard of DDoS attacks, right? So you must have heard of the distributed denial of service attack. So typically, this is an attack that is used by attackers to kind of exhaust the bandwidth, typically bandwidth as well as maybe the computational resources at a server. Okay, and what that does is that because the attack traffic is filling up all the bandwidth towards the server, legitimate traffic cannot get through that, right? So the amount of legitimate traffic will fall down. So that means legitimate users will be denied service from the server. And if attack traffic is filling up a lot of the server's computational resources, right? So typically, if the attackers are usually send TCPs in packets, so they try to initiate TCP connection with the remote server. So if and each TCP connection actually requires a lot of resources. The server has to allocate read and write buffers. It has to allocate state. It has to find out what state this particular client is in, and those kind of things. Like, has the client sent SYN packet? Has the client sent SYNACK packet? So all these kind of things are going to be there. So server's resources are going to be heavily utilized for every TCP connection. So if the attackers are sending a lot of TCP connections towards this particular server, then the server is going to spend more time on the attacker traffic. And typically, when we say attack traffic, this attack traffic is not going to do anything dangerous except for just keeping the server very busy, right? So the server just keeps very busy during a very short period of time. So that's why I said simultaneously. So it's a coordinated attack. So the server is like kept busy for a very short period of time, and it kind of the service capability of the server goes down. So it cannot service any legitimate requests, right? So it's a pretty serious and difficult attack to detect, because the way this attack happens, it is very difficult to distinguish between a real flood of requests coming towards a server versus just some nodes trying to attack the server. So there's a fine line between those things. So that's why this is one of the number one problems that people in the industry as well as people in academia are still quite interested in, although this has been known for a long time. Okay, now let us see what a network admin can do to deal with this kind of things. I mean, how does a network admin use the network traffic analysis to do this? Okay, so one of the ways is that generally network admins have access to the incoming gateways to a given server. That means they know how the data is coming from the internet towards the target server, right? So they actually can count the traffic. They can start by counting the traffic influx from the incoming gateways. And what do you mean by counting traffic? We count, let us say, the TCP SYN packets or the TCP packets or the UDP packets, right? So we have to make a count of how many packets are coming, what is the frequency of the packets. All these things we have to start. The admin has to keep track. Okay. The admin may also have to keep track of the number of IP addresses or the track per IP address flows, right? So if a given IP address is sending a lot of flows or not many flows, so that is a source of suspicion. Okay, so I'm getting a lot of incoming connections, but they're all coming from the same IP address. Then I might know that this is, I might say that this is an IP address that is trying to unnecessarily bombard, the server, right? So again, this requires you to actually look at the incoming IP addresses, like the source IP of packets, and count the different flows. So we'll come to the flows a bit later. Okay. Now, also, how to many times these the admin has to maintain volumetric counters for protocols. So when we say volumetric counters, we basically are saying that how many ICMP packets are coming, how many TCP packets are coming, how many UDP packets are coming, how many HTTP packets are coming. So for different protocols, we may have to keep a track of these things. So this is kind of useful for especially if you want to do anomaly detection, then this kind of volumetric analysis is quite useful. And on top of it, you may have to correlate traffic across these different counters, right? To see if when we say correlate, we are trying to say if so we can do something like a spatial correlation. Okay, for instance, are we getting a lot of ICMP traffic from the same IP address range? Right, so that is one type of spatial correlation, or we can do some kind of a temporal correlation, wherein we say that are we getting a lot of TCP SYN packets at some time in the last five seconds, right? So that's a temporal correlation. This is the kind of tools that the admin has to build to detect these kind of attacks. Okay. The attacker, I mean, the admin may also have to track the DNS activity. So he has to know how many DNS queries are coming, DNS replies are going, those kind of things. And ICMP activity is also very important. Like, are the machines, is the host sending a lot of, not available, not reachable, those kind of messages? Because many times the attackers don't know what service is running. So sometimes they just randomly try to probe, randomly try to flood a port on the server, which may not be offering any service. So again, if the server sends a lot of denial requests for such things, then that is also a possible anomaly in the network. So what I'm saying is, when you, as I said, analyzing traffic is more important. So capturing is only the first beginning step. Okay. Another application is we can use, so building upon the previous thing, we saw that we will need traffic analysis for a lot of things. So we can use, we can build a security tools like Nmap. Okay. So for instance, Nmap uses traffic analysis to provide information like what we saw in the previous slide. So it can help you to, it can do a little more than that. Hello? It can do a little more than just it can do host discovery. It can find out hosts in the network. It can do port scanning of different hosts in the network just to see. So many times a port basically means that it is there is some service running on that particular machine. So many user machines, usually like like say my machine or somebody's laptop or desktop, they're all user machines. So they all have lots of network ports. Okay. Typically, good security practice is to close most of those ports, because your machine is not a server; it is mostly it's just a user machine. So you can actually just you're not providing any service. But the point is, with if there are some ports open and there is by default operating systems like Windows will start running some default services which are not supposed to be run, then attackers can take advantage of such services. So this port scanning, for instance, here can tell you which of the machines are having vulnerable ports, which of them are still open, and those kind of things. The last two things are very important. Actually, this is one of the things I am going to talk about. One is what I call as a service fingerprinting. So many times you have a services, computer may be running different services. A server may be providing a lot of services. But the thing is, you would like to know what kind of service is it? Is it a SQL server? Is it a is it a web server? Is it a database server? If it is database server, what version is it running? So this is all you want to know specific information about the particular service. So that is what is called a service fingerprinting. So Nmap actually provides you those kind of details. Okay, it tells you what service is running, what operating system is, what application is running, what is the version, and those kind of things. Nmap also tells you what kind of operating systems are running on different machines, right? So it checks, it probes. So Nmap actually does the opposite of network capture. It actually it does network injection. Okay, it creates probe packets that are sent to remote machines, right? So network capture is basically we capture data coming into the device. Okay, but if you inject data, that's a different thing. So Nmap actually sends a lot of probe messages to different machines to find out what kind of operating system it might be running. Okay, are you running Linux? Okay, if you're running Linux, it might even go to the level of finding out, are you running Kali Linux, are you running Ubuntu, and those kind of things. Okay, so this is all of this you can do with the libpcap library that we. So what I'm going to say is show you is a small tool. Unfortunately I'm running Windows, so I can't show you this, but you can also all download this tool. The installation instructions are fairly simple. You must install with the super user, and you can mention which interface you want to capture the data on, and then you can apply a lot of filters. So basically, TCP dump is a very interesting tool. It uses PCAP libraries, and it monitors interfaces for outgoing incoming packets. So generally, if you run TCP dump on a given interface, it will capture every data that is coming into and outgoing of that interface. Okay. Now sometimes some packets are not meant for this device. So let me explain this a little bit. So this generally when your device is, say, let's say your computer is connected to the internet, right, or your computer is connected to a let us say local area network, okay, LAN. One of the things that happens is that your computer will only receive data that is meant for your computer, meaning that the MAC address of the incoming packet should match your own MAC address. Okay, that is a link layer MAC address. If it doesn't match, then that your network interface card will discard that packet. Okay, so this is general protocol behavior. Okay, but if you're trying to see, what are the packets that are coming to my device, whether if, say, like, if you're in a local area network, many times due to the sometimes the switch actually broadcasts data on all the links that it has. So you have a Ethernet switch. If the Ethernet switch doesn't know how to reach a given MAC address, it will broadcast the packets in all the links. So in that case, your computer might receive some packets that are not really meant for you. So in that case, if you want to capture those kind of packets, or if you're in a broadcast medium like the wireless 802.11 or Bluetooth and those kind of wireless scenarios, then you must put your network interface card in what is called as a promiscuous mode. So the promiscuous mode tells the network interface card that any packet that comes to this device, if you can sense that signal, you must capture it, and doesn't matter if the MAC address doesn't match or not, capture it and deliver it to the upper layers. Okay. In this case, this packet will be delivered to the TCP dump tool. Okay. Once you are able to capture the data, you can use filters to extract the desired data. So the filters are basically the packet header fields, right? So whatever packet header fields are, like the TCP flags, or the UDP source port number, destination port number, or the IP protocol, or the ICMP error message, or the ICMP host and destination messages, or the HTTP get request. Suppose you can even extract things like HTTP get request. You can see if there are any plain text passwords. So there are lots of recipes to do these things. So we call all those things as recipes or filters. Okay. And TCP dump also lets you to control the size of the data captures. Okay, so you don't have to really capture, if you don't want to capture the entire packet, that's perfectly fine. So I'll just go through this very briefly. This is very boring in the sense that if I'm not showing you, it doesn't, I know it doesn't excite you that much, but I'm sure that you can try it out. Let us say you want to capture data to and from a host IP address, then you can just mention the host now, on a thing here. So if you are getting, so suppose this host is your own host, or you are able to, your admin who's having some control on this host, you may get data that is going out of this host also, right? So otherwise, if you're trying to monitor only your local interface, this will actually get you the data that is coming from this host. Okay. You can also say, you can also mention specific IP address with TCP dump SRC, the IP address and destination, this IP address. Okay. You can also filter the TCP IP, the data by the port numbers, like for all the data that is going or coming into this port, for instance. And for specific source destination, you have to say SRC and tell the port number. This is, for instance, SMTP port number, right? So you can get all the data that is going in or out of the SMTP port, that is the email traffic. Okay. And you can also get packets by network or subnet. You just use the net command here. So you use TCP dump followed by net, and you mention the network, right? So this is the network prefix, and you mention the subnet mask here. Right? This is 24 bits is the subnet mask. You can, of course, because TCP dump is a very powerful tool. So I would say that TCP dump, the way you treat things like TCP dump, think of it like a programming language, right? So it's got a lot of switches. So all you have to do is program around those switches. Okay, so you just look at these options. Each option gives you one way to execute the program. So you can write an entire analysis tool by using those switches inside a nice little C program. So that's how you can utilize it. So one of the switches they TCP dump provides is you can get data by protocol, for instance, right? So you do TCP dump ICMP, you will get all the protocol, all the data by this particular protocol. You can also extract this a bit advanced options. Here it says extract data by the hexadecimal values. So here in this case, you have to look at all these options. -n means don't expand the name to the IP address to the names and those kind of things. So TCP dump actually runs a DNS resolver in the background. So whenever it gets the IP address, it can try to resolve it to a domain name by running a reverse DNS query. Or if it gets a domain name, it can try to resolve it to the IP address. So those kind of things can make it slow. Can make it run a bit slow. So you can actually remove those things by putting -n and those kind of things. So this is the switches you use, and for instance, if I want to capture the SSL, the secure sockets layer encrypted data, you can run it on port 443 and you'll get those you can also get data based on content. Suppose you want to get packets that are less than a particular size. So for instance, you say less and you say you'll get those packets. Okay. If you want to write the output to a given file, you can do directly. So the -w acts like a pipe. So says TCP dump port, and if -w will actually open a channel. It will just open a pipe to this particular file that you provide, and it'll write what is called a PCAP file or a packet capture file, which is just a list of array of packets that are you can just read one packet after another. There are, if you see in the PCAP library, there are functions called next PCAP and things like that. So whenever you pass some string to this particular library, it will actually skim through this PCAP file and get the packets one after another. Okay. And if you want to read from packet capture file, I could have actually shown this one. I have lots of PCAP files on my machine. So you can just mention -r and it'll read that. So you want TCP dump to display a captured file, and you want to extract some data and write to some Python file. You can take this whole thing inside Python. You can use that os.system call, right? So in Python you have those calls, right? So you put this whole thing inside that, and OS will execute that the system call, and whatever output you want to output to a given file or given a screen or whatever, you'll do it for you. Okay, so this is how it's the nitty-gritty of packet capture and traffic analysis. Now comes the real part where we actually start talking about the analysis. Okay, I'm not a data scientist or a machine learning person. I'm a networking person, so I'm not going to talk about all the fancy things people so I'm not that interested in those kind of things. So what I'm interested in is when I'm trying to analyze given network traffic, I want to know what are the features that are of real interest to me. Okay, so one feature that is always of interest is the size of the packets. Okay, this is a very important feature. The second thing is the number of packets. Okay, so this can be put in different contexts. For instance, I can say size of the ICMP packets, or I can say size of the UDP packets, or I can say size of the TCP packets, right? So I can put all of these features into different contexts. What I'm saying is these are general features, and they can be put in different protocol and different layer context, and gives you the necessary intuition to understand the particular kind of traffic. Okay. Then we have the type of packets, like what kind of packets are you receiving. Then these two features you won't find many places. So I think most of you might be familiar with the distinction between control and data traffic. So let me explain. So for the benefit of those who don't. So control traffic is that traffic that actually is exchanged between, say, two machines to set up certain things. Okay. For instance, if you think about the TCP SYN data, where TCP SYN packets which are used to set up the connection, then those are actually control traffic, right? So they are actually setting up the connection, and after that data will flow between the two machines. Then there are lots of other control traffic that go that actually we can see on the local area networks or on the internet. For instance, all the routing protocol messages that are exchanged to set up the forwarding tables, right? All the algorithms that are run before the forwarding tables or the routing tables are established. That's also control traffic. Okay, or anything like a DHCP traffic or ARP traffic or ICMP traffic. All of these are they don't really carry the user data. They are all control traffic. So one of the very important characteristic of network traffic is how much control traffic is it generating, right? So if I'm looking at a device, I want to know, is it generating a lot of control traffic, or what is it, and what kind of control traffic is it generating? So those kind of features are very of great interest to me. Okay. For instance, a device could be trying to discover other devices in the network, which it should not be doing, right? So those kind of things are what we need to see. And data traffic is like the volume of the traffic, like user data, like email messages or videos or any traffic, right? So we are usually interested in the volume of such data. Okay. Sometimes we are also interested in the nature of such data, like is the device exchanging plain text data, or is it exchanging binary data, or is it exchanging XML data, or is it exchanging JSON data, or is it exchanging encrypted data? So those are the other kind of interest we have in this kind of data traffic. Okay. Then we have the number of flows. So the flows, I'll come to it in a moment. So it's actually when we think of two machines as two ends of a pipe. So typically we assume that a flow is basically data flowing from one machine to another. Okay. And we characterize it with different kinds of we can put IP address, source IP address, source destination. So I'll explain that in a moment. It's in the next slide. We're also interested in header space analysis, like what are the headers, what are the header fields, and what are the options. So many packets. If you see TCP, for instance, has a lot of features that are rarely used. Even IP has such features. Most of the network interface devices cards will ignore say device drivers in your machine will ignore those options because they don't have any meaning for the receiver. So, but the thing is, we sometimes for a security analyst or a network analyst, those are very interesting features, right? So maybe there is something that the attacker is trying to do using those features. Okay. Sometimes you can send a badly formed packet to a machine, and if the particular driver is not well formed, it hasn't really anticipated these fields, then that particular machine could crash. Okay, so those are the kind of things that's why the header space analysis is very important. And the last one is again, this is similar to the data traffic, but it's more talking about this is called payload analysis. So this is typically when we say payload, we are talking about what we call as the application payload, okay, or the TCP payload. So payload is the actual messages that are sent by the device, so or the user. Okay, so payload analysis is very interesting. There is a whole area of research in payload analysis called deep packet inspection. So or layer 7 inspection. So where people actually try to figure out the structure of proprietary protocols. Like if Skype is using a proprietary protocol, we want to know how it is actually exchanging the data, how it is actually controlling the Skype sessions, how Microsoft Teams is doing its connections. So those are the kind of things you could do when you want to, when you do payload analysis. Those are the kind of applications you can think of. The second interesting thing, so packet analysis is usually done when we try to do one packet at a time, but we would also like to do flow analysis. Flow analysis of when we talk about a group of packets. Okay, so this is a common definition. Okay, it's not the standard definition. There is no such standard for standard definition flow analysis, but this is something I've used most of the time in my research. So something like we say source IP, source port, destination IP, destination port protocol. So 5 tuple. Okay. So what I'm saying is that I can, if it is a flow is unidirectional, that means I assign a value to source IP, source port. So any packet that has a given source IP, source port, destination IP, destination port, and it is using a particular protocol. I call it as a unidirectional flow. Otherwise, if I can exchange these things, and I can always consider the reverse direction, right? The destination IP address could actually be replying back to the source IP. So in that case, that's a bidirectional flow. So I can consider both as part of the same flow. So flows can be either unidirectional or bidirectional. So what are the features that are of great interest to us in flow analysis? So one of the things that is interest is the size of data exchanged. Okay, so what is the volume of data exchanged in a given flow? We want to know how many flows are exchanging. Suppose you have a flow of 100% in the network. Okay, so one of the things that people try to, especially people who are working in the flow policing or flow shaping kind of applications, they want to know how many flows are occupying less than 10% of the bandwidth, right? Let's say there are lots of flows that only send, say if I have 100 Mbps bandwidth, there will be lots of flows that might be sending less than 1 Mbps per second. So let us say there are 50 such flows, then basically I can say that 50% of the flows are occupying less than 10% of the bandwidth, right? Because each flow is sending only 1 Mbps. Okay, so those kind of things are of interest to us. Then the other thing is how many packets of a given type or a given protocol are exchanged in this. But typically the protocol is fixed here, but you can count the number of packets in a given period or a given in a given context, for instance, okay, or a given session or whatever. The third is more to do with timing analysis. So it talks about frequency of packets, like what is the frequency in which the packets are arriving or being replied at. So the inter-arrival times, the variation in the time between the different packets, all of these are actually interesting features that contribute towards the flow analysis. Okay. And what is flow analysis? Typically they try to actually, for instance, here something where you can use flow analysis, right? For instance, for port scanning, you can use general. You can look at a sequence of. You can try to check for sequence or pattern of port numbers of in incoming packets, right? So that is one way to see if somebody is. So port scanning is basically some machine is trying to, some remote person is trying to scan your machine's port numbers. Maybe it can be sequential, like 1, 2, 3. But it can also be, you could also be scanned in a pattern like 1, then 3, and then 5, or you could be scanned in like 2, 4, 6. So there are some patterns, right? So attackers use all these obfuscated patterns to escape from detection. But so one and network analyst, for instance, can check for can try out different patterns and see if the machine is being port scanned or not. DDoS attacks, for instance, how you can use flow or packet analysis. You can check for incoming packets on same port IP and count the number of packets, right? So I already talked about how DDoS attacks can actually be detected and things like that, right? So now what I would like to do is there are more tools you can try. Wireshark with the user interface, T-Shark without your LeapPcap. So what I want to talk about is I'll talk about what the work we have done in Internet of Things, which involves a lot of network traffic analysis, and it applies to solving a special problem called fingerprinting. So I could just stop here just to pause for any questions. So any questions anyone has? Okay.
Sir, I have one question, sir.
Please.
Sir, when the network comes into the cloud, then how these all our tools can be used for handling traffic in the cloud, sir?
So you have to be specific with your question. When you say network comes into the cloud, what do you mean by that?
Some the network devices when we are using in the cloud domain. Suppose the huge number of computation are going on and network communication is happening, then how that all are we can handle using these tools?
See, are you talking about SDN kind of situation, or are you just talking about cloud providing you some? Because cloud mostly provides computational resources, right?
Yes, sir. Yes, sir.
So when see the devices and tools don't change. Like you may have a bigger router there, which actually be where you will be running this which will provide this high speed connectivity, right? So most of the routers
Yes.
Cisco provides, for instance, has all these features. They have a protocol called NetFlow that actually captures a lot of these features I talked about.
Okay, sir. Is there is separated tools available for particularly for cloud, or these network tools are can be used for the cloud also, sir?
they can be used. So the only thing is, if you have a lot of
Oh,
volume of data, what happens is that
okay,
you
sir.
have to put some boundary on how much you want to capture, right?
Okay, sir.
So the tools don't change. I mean, there'll be just the user interfaces will change, but the basic tools like the underlying OS level, the library, the libpcap is the one that actually works for a lot of things. So if you take any fancy tool that Cisco implements, it will still be relying on the Berkeley sockets, BSD, and the libpcap libraries only. It won't be having any of its. There may be some optimizations and all that to make it run faster, because routers are not user devices. You can actually have a faster operating system on that, right? So those kind
Yes,
of things are,
sir.
right? But otherwise the tools don't change much. You just remember, when you want to do capture, you must be on the, either you are a router through which the data is passing. Okay, you can capture data like that, or if you are an end device, you can capture device that is coming in and going out of your device, right? So that is how you should look at
Okay.
this.
Okay, sir. Okay. Okay.
And the big data, and if you want to do large volume analysis, that's actually a pretty good question. How do you count the number of flows? If you are having like 1,000 or million flows, how do you keep track of them? How do you
Yes, sir.
count all these things I just talked about, right? That's a big research area,
Okay, sir.
right?
Okay,
So
sir. Okay.
I mean, high speed flow identification, high speed flow analysis is non-trivial effort. You need algorithmic structures that let you capture and store all this data. Many times we actually have to create a number of buckets equal to the number of flows. So and every time you get a new packet that corresponds to a given flow, you may have to update the corresponding bucket. So you must remember, all of these happen on these buckets are in memory. So you have to store them. If they are in hard disk, then how do you retrieve them? So many things are there, right? So it can quickly become very
Okay.
uh, slow. So yeah, that's actually a good area of research to look at. If you are getting a lot of data, how do you manage the flow? So there are
Yeah.
resources,
Yes.
there are people who have done some work on this.
Okay, sir. Okay. Thank you, sir.
Sure. Any other questions, please? So right now, if I didn't mention about things like software defined networking and things like that. So there, for instance, because I didn't talk about the different types of networks, right? So my assumption was that we are using a conventional. We either we are part of a network like at home network or some campus network. But if you see in the future, like in 5 years down the line, all the campus networks will be replaced with this cloud-based or software-based control. So there, the thing is that the data, it doesn't mean that all the data goes to the cloud. It's just that the control comes from a different part of the network. Okay, so all the control plane will be actually managed by one software agent. So that is the only difference. So there again, the issues. I mean, uh, all the routers, switches inside the campus will remain as it is. There will be little. They will be consuming less power and have less capabilities, but they all provide all these packet capture data and everything. So that's actually an interesting paradigm that you will see very very soon. Okay. So if there are no more questions, let me talk about. Yeah, any questions? Anybody else? Please feel free. I'm sorry I came in a bit late. I had a bit of trouble with the Teams. I have my own university account which also uses Teams, and it was interfering, and so yeah. But yeah. Please feel free to pause at any given point of time. Okay. So let me talk about a little problem here. Okay. So let us say that you have a set of devices. You must have heard of the Internet of Things, right? So basically, the Internet of Things is a paradigm wherein you have lots of you have devices, and these devices, let us say something like your smart TV, for instance, connects to the internet, right? So gets all the data from the internet. So these devices are basically connected to the internet, provide service to you, provide you can control the devices from the internet, or you can control using a mobile app. So a lot of things they actually give you a lot of service. So they are not actually full-fledged computers, but they are capable of processing the user commands and things like that. Okay. So one of the problems that happens is that suppose so one of the interesting problems in this area is that how do I know if I look at the traffic, can I identify that this particular traffic belongs to this particular device or not? Okay. So this is a very interesting problem that is posed in literature, in the community, right? So people want to know how to. So we call this problem as fingerprinting. Okay. So, and specifically, we call it as a device type fingerprinting. So, because device type means the type of a device can be something like a camera or a smart bulb or smart TV, right? So, we want to have a tool that looks at the traffic from a given device and says, oh, this traffic must be coming from a camera, right? Or it says this traffic must be coming from a smart TV, right? So, this is the problem that we have looked at. And as you can imagine, it involves a lot of traffic analysis, right? So without going into too much details of the research, I'll talk about what we actually did. So this is a threat model. So why we do this and all that. Like devices can be replaced, or devices can be compromised and things like that. I mean, there are a whole bunch of reasons people will give that, okay, these devices don't have strong authentication, they are not secure. Okay, all the stuff is fine, but the main thing is that these devices are usually easy to replace. Okay, so in the past, people have tried to do this. These are all, again, very interesting network layer, network traffic analysis, right? So I just listed a few under different categories. So, for instance, how did people fingerprint devices in the past? Okay, so one of the ways people did was that, let us say, you can try this experiment. You can take your Wi-Fi access point. You can actually run a PCAP library, PCAP tool, Wireshark or T-Shark, and what you need to do is measure the inter-arrival times of the packets. Okay, like you just check the look at the link layer frames, look at the timestamp, and take the difference between two consecutively collected packets, right? And create some vector out of it. And on this, you can actually run some kind of a regression or some kind of tool. And typically what happens is this particular data that you just got will actually correspond to the pattern by which your access point is sending out its beacons, right? So because generally access points send out a lot of things. They just not just beacons, they send out data traffic, they send out replies and everything, right? So this is how people people figured out that different access points actually have different ways of sending out beacons. There are variations, small variations like millisecond, microsecond variations that could be actually used to fingerprint a specific kind of device. Okay. So the second one is also similar. It looks at the link layer scans and things like that. But this one actually looks at the device driver variations, because TP-Link or Qualcomm, D-Link, Cisco, they all have different people who are implementing their devices, and all of them use different kinds of memory models or data structures and things like that, right? So that means there is some variation in the way in which they can implement the same protocol, 802.11, same protocol, but the way they do these things, the physical implementation gives some variations. Okay. People try to actually physically fingerprint devices, meaning that they want to say this is a particular device, and I can. So for that, they looked at, this is not network analysis, but the first one is actually radiometric data, which is that radio signals and things like that. The second one is actually related to network analysis. So basically, there's a feature called as a clock skew. The beauty about clock skew is that it was discovered in 1999, or it was known in 1999. Basically, every device in the world has its own clock skew. Okay, so that means because a clock skew means how it's the rate of it's the rate at which your clock actually differs from the actual standard clock. Okay, let us say there's a standard global clock. Your computer will also have some standard. Your computer has some kind of a clock, right? So this clock skew actually tells you how fast or slow I'm from that particular clock. Okay. So that's a very interesting feature. It actually uniquely identifies the device. This is the last one is very important, which is basically how to do how to check. It's called protocol specific fingerprinting. So we actually look at the variations of protocols across the same protocols across different devices. Okay, this is actually the layer 7 fingerprinting I talked about. That is application layer. Okay, so because it needs to analyze the protocol grammar, syntax, and things like that. So, so I won't get into all of these things. So basically what I'll get in is how we actually did this fingerprinting and what we did. So the key observation is that IoT devices usually have well-defined set of functions, and we call these functions as network behavior. And typically we can actually capture these behavioral patterns and we can learn. Okay, so this is how we can look at it. Let us say this is a device. Okay, the top part, the B1, B2, B3 are the different device behaviors, right? That means so you are say watching a TV, Netflix. So B1 could be when you switch on Netflix. B2 could be when you switch on to normal cable. B3 could be when when the device switches on to Hotstar or something. So I'm just giving a very coarse example. They may not be real behaviors, but something like that. Suppose you have a smart light and you're changing the colors. Then B1 could be one color, B3 could be one change of another color. So like that. Okay. So many times it's how much the observer can observe is the main thing here. So if the observer can observe only few things, then he's going to observe only the sample of the space, right? So this is the traffic he's going to observe. So each behavior here, for instance, corresponds to sequence of packets during the time that the observer is observing. Okay. So for instance, B1 could be a sequence of 10 packets, B3 could be a sequence of 10 packets, right? B4 could be a sequence of 10 packets. Okay. So in this case, the behavior observed is B1, B3, and B4. Okay. So now, how do we use this information to capture the data? So without getting into the details of what there's a lot of analysis that has gone in this thing. I'll give you the brief of how to take the network data and model it into a real problem, right? So what we did is that a packet contains headers as well as payload. So essentially we divided the behavior of the device into two parts. One is the packet header analysis, which actually gives you the control information in a static or a structural sense. Okay, and the second is the payload feature, right? So payload is basically the application payload, right? So it gives you indication of the dynamic behavior of the device, because the data is the data that the device sends out depends on the what the device is being asked, right? It's like a natural way the device is responding. It's like a protocol reply. Okay, so these two actually correspond to the features that are of interest to us. One corresponds to static or structural. The second one corresponds to dynamic or behavioral data. Okay, so in essence, what is the behavior we are talking about of a device? It's a set of network features that are combined with static features and the dynamic features. So these are the features that we actually looked at. Okay, so if you see here the link layers, so I separated the layer features in terms of layers. You have link layer, network layer, IP layer, transport, and here we basically these are the features I'm looking for. So when I'm saying features, I'm just saying that given a packet, I want to know if it is ARP packet or not, right? And in the same packet, it could be IP packet as well. So in this case, these are all binary features. So it will be 0 or 1. So if I capture a packet, if it is ARP packet, then under that particular thing, I'll put 0. right? If it's also an IP packet, I'll put 1. If it is ICMP packet, I'll put another 1 there. If it is not ICMP packet, I put a 0 there, right? So like that, all these things these are all binary values. I see if it's a TCP or UDP packet. And so all the top features like this from the top to the last but second row, these are all static. They're all binary features like 0, 1, 0, 1, 0, 1. So that's why I call them a static or a structural features. The last one is actually payload dependent. Okay, so these are features that we felt that reflect the behavior of a IoT device. Okay, so this payload we mean the TCP payload or UDP payload. Okay, so out of these, so instead of actually trying to examine the payload itself, so we design features that are actually reflective of the payload nature. Okay, for instance, we looked at the payload length. Now, payload length is easily accessible even for encrypted data, right? You don't have to actually decrypt any packet to get the payload length, right? But that's a good indicator of how the device is communicating. The second is payload entropy, which is actually a field that tells you how the device messages are being exchanged. So devices which exchange plain text messages usually have the payload entropy of such messages very less. If the device exchanges binary messages like XML or JSON, those kind of things, then the entropy is higher than the text messages. And if the device exchanges encrypted messages, then the entropy is the highest. Okay, because encryption adds a lot of randomness to the message. Things like TCP window size, for instance, if it's a TCP packet, the window size is actually a very interesting feature. It tells you the capability of the device, how capable is the device in processing the data. So whenever you see TCP is the layer that is just below the application layer, right? So when the data comes into the device, the application layer running on the device should actually read from the TCP buffer. So if the application on the device is slow or if it is busy with something, then it will not read this application buffer. So when the device actually advertises the TCP window, it is actually advertising this particular buffer space, right? So this part, it also advertises the congestion window, but in this case, for smaller devices in the IoT domain, this usually is a combination of both the flow as well as the congestion control. So this window size is actually defined by that. So this is actually a good indicator of whether the device is capable of fast processing or slow processing. Okay, so these are the key 3 features that we looked at, and this is described. And we also did some kind of a estimation, statistical estimate. This is what is called as the ECDF plot. Basically, it's a cumulative plot. It always, the value always goes to be 1. For instance, we plotted the payload. This is a payload entropy for a given device. You can see that let us say TP link here is the black one. So here what it means is that the fraction of the data that have a feature value here, for instance, 10% of the if you look at something like this here, 10% that they only less than 10% that they of this device data has this value less than 0.8. It falls between 0.6 and 0.8, and majority of the device traffic actually has the entropy between 0.8 and 0.1, right? So this is a cumulative, ECDF is a cumulative distribution plot. It's useful. So how to read this plot? The plot is that these three lines should be completely separate from each other, right? So if these are interesting features, if this feature is a good discriminator, then these 3 lines will be separate from each other. As you can see, the lines are rather separate from each other, so it actually gives you a way to use a statistical classifier to separate these, right? So you can use some kind of a machine learning simple machine learning classifier like a KNN or decision tree, and get you can actually distinguish between them. Okay. So, yeah, I think just want to. I'm already beyond the time. Let me just skip to the end. So this is just telling you how to, how the features are and things like that. I don't want. There's no need to get into this. So we basically, how do we do this? Is that we model it as distinct command sequence response sequences, and then we call each command. Hello? Can you hear me?
We can hear
Yes,
you.
sir.
Yes, sir. Yes, sir.
It's somehow my machine is just hung up. So just give me a second. Okay, we're back. So our approach is simple. So we basically look at device behavior as a command response sequence, and we talk about a session. This again, I haven't defined it. I know it's a very interesting thing. Uh, Session is so it's just you can think of it as proof of packet exchange in a given activity, right? So just to that's what we call it a session. Okay. So we basically did some empirical analysis. Hello.
Yes, sir.
My presentation has gone, right?
Yes, sir.
Oh, yeah. So just give me a second. I'll just open it again. Just crashed.
Ah. Hello, sir. Yeah, now it is visible, sir.
Yeah, I just reopened it. Okay, so I wanted to talk about this data collection and the setup we had for data collection. Okay, so here you can see that. So what we did is that we experimented with each device. That means we just switched on the device, switched it off, and we communicated with it and sent some commands to it, and then collected the data. So this is how we did that. All the devices actually connected to the to access point that we were running on this particular port here on the switching network, and basically the packet capture module actually was running on top of this. So here's the fingerprinting module that was actually reading the packets from the packet capture module and trying to fingerprint the device. Okay, so this is the actual running setup. You have Kali Linux, and then you have what is called a host APD, because we wanted to use a access point that is running on us. We want to use a laptop as access point. That's why we ran this host APD and and Open vSwitch. So this basically provided the services to all these devices. Okay. So you can see that here is a hand that is communicating, and it controls this particular device like a light or something like that, or music or anything. So we collected the data by just experimenting with it, and then trying a few things and checking for its behavior. And in the end, basically, the rest of it is fairly straightforward. Once you have the data, we used a supervised learning method to actually train the classifiers. So we have a bunch of classifiers we trained on these individual devices. It's called a one versus all kind of training, wherein the traffic of one device is to be set as a positive, and all the remaining traffic are set to be negative. So that's what it means. So here this is the type of traffic we collected. This is different data instances. Like we used 5 packets as one data instance. That means 5 packets coming from the source IP as a one feature vector, right? So then yeah, so remaining things are fairly straightforward. How we do this classification, true positive rate and accuracy. And so basically true positive rate is the ability to correctly identify the data instance, and given us the how many of the correct instances, how many are correctly identified is true positive, how many were not identified is a false negative. So this is the thing. And so we got about pretty good accuracy and all that. But yeah, the whole idea is that we were able to model a problem in the terms of traffic, and able to get these kind of results. So yeah, so that's I think I'm already I overshot your time by a lot of things. So I think I'll stop here and take any questions that you may have regarding